Let's move on to the last topic of our unit in preparation for next Tuesday's test. Let me draw you a picture, and then let's work through a couple of things on that picture, okay? Let's say we've got a ball that's being dropped. So it starts at a speed, Nicole, of 0 meters per second. There's a ground down here. That ball is going to fall towards the ground because it's dropped straight down. It's going to fall towards the ground a distance of 10 meters. Let's say I want to find out how fast that ball is moving when it reaches the ground. How would I do that question? How would you do that question right now? Clearly, I'm going somewhere with this and you're going to learn something different here today. But how would you do that question right now if I didn't teach you anything different? Yep. Yeah, you know the acceleration is negative 9.81. So where would you go with that? Group B, yes, absolutely. It's a group B problem. It accelerates. We have VI, we have VF. Oh, sorry, we're looking for VF. We have A, we got D. So probably use VF squared is equal to VI squared plus 2AD. Does that make sense? That's nothing new, right? You did that early on in September. VF squared is equal to VI squared plus 2AD. In fact, we've done so many problems this year where we keep going back to that equation. That seems to be honest, probably the most common group B equation that we have. But let me show you another way of doing this question, all right? A way that is not necessarily better for this particular problem, but can be a little bit more versatile for other problems. It's a bigger, more general concept. Let me ask you this question. When this ball is at a height of 10 meters before it starts moving, just before it's dropped, what type of energy does it have? Potential. What kind of potential? Gravitational potential energy. So we're going to say up here, it's got MGH. Agree? We'll call it MGH initial because that's the initial height. Clearly the height changes. So there's going to be a final height and a in the middle height and so on, but this would be the initial height. All right, let's fast forward now a couple seconds till it reaches the ground. What kind of energy does it have when it reaches the ground at the bottom? Not after it hits, but what kind of energy does it have when it hits? The moment that it hits, Nick? It has kinetic energy. It's moving, right? If we're looking for the speed at the bottom, then we know it's got to be moving when it hits, not after, but when it hits. And if it's moving, then it's going to have kinetic energy. So we're going to say the bottom energy, the final energy, is a 1/2 mVF squared. VF being the final speed, because VI, of course, was 0 meters per second. Good? What do you think the relationship is between these two energies? What do you think the relationship is between the initial potential energy that this ball had 10 meters above the ground and the final kinetic energy that it has as it strikes the ground? Holly? Good. Good. We have a transformation of energy taking place here. We transform gravitational potential energy into kinetic energy. We can't just get kinetic energy from nothing. It has to come from something. It comes from the gravitational potential energy. So it's a conversion. Gravitational potential energy decreases, kinetic energy increases. Good. So what do you think the value of the final kinetic energy is relative to the initial potential energy? If potential is converted to kinetic, how do you think the values of the final kinetic and the initial potential compare? They are the same. They're the same. That's what we call the law of conservation of mechanical energy. The law of conservation of energy says you can't create energy. You can't destroy energy. You learned about that last year in Science 10, called the first law of thermodynamics. It's the same thing. You can't create energy. You can't destroy energy. You can only transform energy from one type to another. Now, if we account for all the types of energy, then we know that the final energy, whatever it is, whatever kind it is, has got to be equal to the initial energy, whatever kind that is. So what we would do if we wanted to solve this problem a little bit differently than VF squared is equal to VI squared plus 2AD is set EI equal to EF. What kind of energy do we have at the beginning here? At EI, At the top, gravitational potential energy. What kind do we have at the end? Kinetic energy. Make sense? Now, how would this change if this wasn't dropped from a speed of 0 meters per second? What if it was thrown downwards at a speed of, let's say, 10 meters per second? Does the equation we use change? No, not at all. It's still a group B problem. We still have a VI, except that VI is a different value than it was before. Still use the exact same equation. The answer, of course, is going to be different. When we go over here to the right-hand side, the green problem, the conservation of energy problem, things change a little bit. What kind of energy do we have at the top? Well, we got potential because it's got a height. We also have kinetic, right? Because it's moving. We'll say 1/2 mvi squared versus kinetic at the bottom, which is 1/2 mvf squared. We'll still say EI equals EF. That's the law of conservation of energy. The total amount of energy will remain the same. You can't create or destroy. You just transform potential energy at the top into kinetic energy at the bottom. We got more kinetic energy at the bottom now than we had in the last case, right? Because we started with kinetic. We still have that amount of kinetic, but now we also have the additional potential energy converted to kinetic energy. How does this change? Instead of EI, still have EI equals EF, but instead of mgh equals 1/2 mv squared, now we've got mgh initial because we've got potential energy at the beginning plus kinetic energy, 1/2 mvi squared equals 1/2 mvf squared. Now you could solve for vf in this equation the same way as you could solve for it in the group B equation that we showed you before. Make sense? I don't know about you. This one seems a little bit more complicated than the first one, right? Should we use this method to solve this problem? Whatever. If you'd rather use VF squared is equal to VI squared, go ahead. But you're going to see over the next couple of days that the method that I just showed you is a little bit more versatile for certain things. And in the end, if you take a step back from it for a second, it ends up being the same thing. Exactly the same thing. Let me show you something. You don't have to write this down if you don't want to. Just a little off to the side kind of thing. What can you do with the masses here? Cancel them out. Appears in every term, right? So now I've got GH initial plus 1/2 mvi squared equals 1/2 vf squared. It's a little bit simpler now, right? Sorry? There's no m in the second one? Oh, right here you mean. Yes, you're right. Thank you. Good? Okay, let's rearrange this a little bit here. Let's say, you know what? Let's change the order of this. Let's say 1/2 vf squared equals 1/2 vi squared plus gh initial. Can we do that? That's exactly the same thing, right? I'm just putting what was on the right-hand side over on the left-hand side and what was on the left-hand side over on the right-hand side. Now, we're allowed to do whatever we want to do to this as long as we do it to every term, right? In the last case back here, we divided every term by mass. That was fine as long as we divide every term by mass. Can't just divide one or two terms. It's got to be all of them. We could have divided every term by 3,112. It wouldn't have made any sense to do that, but we could have. That would have been mathematically legal. Okay. What we can also do, and makes a little bit more sense, is to multiply every term by 2. Okay. If I multiply 1/2 vf squared by 2, what do I get? Vf squared. If I multiply 1/2 vi squared by 2, what do I get? Vi squared. If I multiply gh by 2, what do I get? 2gh. Have a look at that equation now. Vf squared is equal to vi squared plus 2gh. What is that the same thing as? Vf squared is equal to vi squared plus 2ad. My height being my displacement there. Does that make sense? So again, you don't have to write down what's in black there. I just want to show you that in the end, even if we think of it a little bit differently here and do it using conservation of energy, it ends up being the same thing as my group B equation. Listen, this is such a huge concept over the next year of physics for you, the next year and a half of physics for you, conservation of energy. Not necessarily dropping a ball from a certain height. Okay, conservation of energy rears its ugly head many, many times in many different contexts. It's such a big concept. It goes all through physics. You can see here maybe now why VF squared is equal to VI squared plus 2AD ends up being probably the most common group B equation that we end up using, because it's based on this law of conservation of energy, which ends up being so big in physics. All right? I'm going to give you a few notes here, and then we'll do a couple examples. A couple more general examples, or I should say a couple more specific examples. Situations where the object isn't falling straight down, situations where the object isn't being just dropped, and so on. So here's what the law of conservation of energy says. What you're going to write down here over the next couple minutes is just a summary of what we've already said, but we just didn't write it down in words. Energy can't be created and it can't be destroyed, but it can be transformed from one type to another. So in the last situation, when we dropped the object, we had a conversion or transformation of gravitational potential energy into kinetic. Even when we threw the object down, we started with potential and kinetic this time, but the conversion was still potential to kinetic energy. But because the energy can't be created or destroyed, the total amount of energy that we ended with was equal to the total amount of energy that we started with. In fact, we could have asked you to find the speed of the ball halfway down, because the energy halfway down was exactly the same as well. Total amount of energy anywhere along that path is going to be the same, because you can't create or destroy energy. Now, sometimes we end up with a little bit more energy at the end than we started with. We didn't in the example that I just showed you, but sometimes that can happen. But if it does happen, if we do end up with more energy than we started with, it's not because we created energy. It's because it was added from something else. It's because we didn't account for something. Wind might cause something to speed up and make it appear as if energy has been created, but it hasn't been created. It's just that we maybe didn't account for the wind. Similarly, sometimes it may look like energy is destroyed. If I drop a ball on the ground, the ball eventually comes to a stop, right? Where'd the energy go? The kinetic energy must have been destroyed. No, it wasn't destroyed at all. Where did it go? Well, when you drop the ball, this might be hard to believe, but when we drop the ball on the earth, the ball moved the earth. Some of the kinetic energy from the ball was transferred to the earth, and the earth shook a little bit. Why didn't you feel it? Yeah. The mass of the ball that you dropped is so small compared to the mass of the earth that transfer that kinetic energy to the earth, you're never going to feel it. Now, the reality is, when you drop that ball and it hits the earth, it's not all transferred to the earth. You lose some as well due to heat and sound. It's not destroyed. But if you bounce the ball enough on the ground, the ball gets a little bit warmer. Some of that kinetic energy was transformed into thermal energy. It looks like sometimes it was destroyed. Drop the ball, it stops. But the kinetic energy wasn't destroyed. It was just transformed into kinetic energy in the earth and thermal energy, heat energy, as the ball itself warms up. A little bit of sound energy too, because you hear the ball hitting the ground, right? Mostly heat, a little bit of sound there as well. Again, never created or destroyed. Sometimes it just looks like it's created. Sometimes it looks like it gets destroyed. Usually when we solve a problem in Physics 20, we're going to have a negligible. What do we mean by negligible? What's that word mean? Not very much. so small amount that it really doesn't matter. If we solve problems, which we're going to do, with a negligible amount of energy added or taken away from the system, like there's no wind, there's no friction, there's nothing to take energy away from the system or to add energy to the system, or at least so small that it doesn't matter, then all we're going to do every single time is say EI equals EF. That's exactly what we did in the example that I showed you a minute ago. It's exactly what turned into VF squared is equal to VI squared plus 2AD. Let's have a look at an example. This is much like the example that we just did, except we hadn't actually calculated the value in the problem that we were just looking at. So it says a 500-gram ball was thrown downward at a speed of 5 meters per second from a height of 35 meters. We want to find the speed of the ball as it hits the ground. Now, we know that we could use VF squared is equal to VI squared plus 2AD to solve this question. It's a group B problem, right? We're not going to, because I want to give you experience with conservation of energy. But we know that we could. All right, what do we got here? We got a mass of 500 grams, which we're going to convert to kilograms, 0.500 kilograms. We know that we have an initial speed of 5.00 meters per second. In fact, we know that we have an initial velocity of negative 5.00 meters per second, right? Because it's thrown downwards. We know that my initial height is 35 meters, or I could say my displacement is negative 35 meters. We want to find the speed of the ball as it hits the ground. Solving for this using conservation of energy, I'm going to say EI equals EF. I'm going to change this actually. Instead of delta D is negative 35, what should I call it? HI, the initial height, negative 35 meters? No, the displacement was 35 meters. The initial height is 35 meters. EI equals EF. What kind of energy do we have at the beginning of this problem? Kinetic and potential energy because it's moving and it's got a height. Ask yourself, when you're doing one of these problems, ask yourself at both points, the initial and the final, is it moving? The answer is yes, it's got kinetic. Is there a height? If the answer is yes, it's got gravitational potential. At the end of the problem, as it hits the ground, it's got kinetic energy. We can cancel out the mass because it appears in every term. Let's plug in some numbers here. Usually I like to rearrange and then sub in numbers, but for these problems, I usually sub in the numbers right away. VI is 5.00. Why did I drop the negative there? Sorry? Yeah, I want absolute values, but why specifically in this case do I want an absolute value? Why would I never plug in negative 5 for that? VI, negative 5 meters per second, is initial what? No. Sorry, it's initial speed right here. Yes, it is. Yes, it is. But in my givens, the way that I have it written down, it's initial velocity, right? VI is negative 5. That's initial velocity. What do I want to plug into this for kinetic energy? Speed. The initial speed is 5 meters per second. The initial velocity is neg 5. The initial speed is pos 5. Let's add to that 9.81 meters per second squared. And we've already established that we always plug that in as an absolute value, as a positive value. HI is 35 meters. Now let's get the number on the left-hand side. Let's say 0.5 times 5 squared is equals. And then let's add to that, use some brackets here, 9.81 times 35 equals. And now we can either multiply that number by 2 to take the half over by multiplying by 2, or we can take the half over by dividing. I'm going to multiply it by 2 this time. If you had divided that by a half, we would have got the same thing. And now we got to square root that. So we do that, we end up getting 26.7 meters per second. What's the direction of that speed? What's the direction of that ball moving? Well, the equation doesn't tell us, right? Because what have we just solved for? Final speed. But we know that if we throw it downward, it's going to be moving downward. So if you were ever asked for the final velocity, then we just tack on a down to the end of it. All right? All right, let's take a look at your fifth and final energy worksheet here now from Google Classroom. And I'd like you to work on questions 1 through 5 right now. 1 through 5. I want to do one more problem with you. You can finish up that worksheet up to question number 5 for homework tonight. Have a look up here, please. We have, in this new question, we have not a ball that's being thrown straight down, but rather we have a hill. Maybe it's a roller coaster. In 2 weeks, or I should say in 12 days, we're going to be on our field trip to the amusement park. We're going to do a problem that's almost exactly like this. Let's say we've got our roller coaster cart at the top of the hill. Let's say its mass is 1,000 kilograms, including a couple passengers. Let's say the height of the hill is 40 meters. Let's say we want to find the speed of this roller coaster halfway down. How fast is the roller coaster moving halfway down this hill? Well, all of a sudden now you look at this question and think, oh, would this be group A or group B? Well, it'd be group B because it's accelerating, but we're not going straight down. We're going on this path that's kind of curving. So, and it's not a nice uniform inclined plane like we did earlier on in this unit. So maybe the best way to do this is conservation of energy. Let's say that EI equals EF. We know that the total energy rate here is equal to the total energy rate here, but it's also equal to the total energy rate here because the total amount of energy has to remain the same if we account for everything. What kind of energy do we have at the beginning of this problem? Kessler? We got potential because there's a height. Ask yourself that question, right? Is there a height? If the answer is yes, then there's potential. If the answer is no, then there's no potential. Is it moving? It should have been. Is it moving? Yeah, it's moving at 2 meters per second. So we've got kinetic energy as well. So we'd say mgh initial plus 1/2 mvi squared equals, what kind of energy does it have halfway down? Does it have a height halfway down? Sure it does. It's got a height of 20 meters halfway down. And is it moving halfway down? Sure it is. Not stopped for sure. We can cancel out masses because it appears in every term. We can say 9.81 times the initial height of 20 meters plus 1/2 of 2.0 squared equals 9.81. So this should have been 40 meters, right? Equals 9.81 times 20 plus 1/2 VF squared. Mathematically a little bit trickier, but doable, right? Now, there's one way that I could have done this to save a little bit of work. Remember we said we could define potential energy relative to whatever we want? If we define it relative to here, then the initial height is 40, the final height is 20. If we defined the potential energy relative to here, which we didn't, but we could have, the initial height would have been 20 and the final height would have been 0. Guess what? We would have got the same answer either way you look at it. All right, we'll leave it there for today. Finish up those 5 questions on the worksheet that you have for homework for tomorrow, and then we'll pick it up there.